Hello and welcome to week 10 of Introduction to Data Science. Let's kick this off like we always do and have a look at what we were learning last week as a very quick recap. In week 9, we started by having a look at logistic regression, and that is when we're trying to predict a categorical output variable that's binary, so it can take 0 or 1. We then had a look at how you can make predictions and how to think about how we can separate our data into training and test sets in order to avoid overfitting. So modeling our data in a way that means that our model is too tightly coupled with the actual data we're training it on. And so it becomes pretty useless when we start trying it on new data that the model hasn't seen before. So we started talking about what overfitting was, and we're going to come back to that this week as well. And then we also started having a look at feature engineering. So how can we use feature engineering, so making changes to our features to improve our models? And one such example was trying to account for any non-linearities in our data, such as taking the log and then using the log to of a feature in our model. So there wasn't many 2 assignments last week, but there is this week. We have the homework, which is always obviously a focus. And the homework, as you should be familiar by now, hopefully you've had a look at it, is to make a really ugly plot, which is always a bit of fun to mark. Then use a new package and describe your use case and how it works to us. And then the last thing is we want you to provide peer feedback on 2 other repositories, projects from other students, and that'll be really useful for them. Your team will also get student feedback so you can get an idea of how other people are viewing your project. And please copy and paste the links to those issues into the homework itself. It's really useful for when we're marking, just to be able to click and follow along to find where your issues are, and that will guarantee that there won't be any issues with being able for us to mark those issues that you created. Okay, let's have a look at some of the questions that we got from the quiz. The questions that you found the most difficult, according to the feedback, was questions 6, 7, and 8. So assessing model fit. So let's just kind of go over those together, and hopefully I can provide a little bit more information as to why certain answers were correct. So the first question asks us to assess this model. It's trying to predict a total annual salary from the number of years that someone has been employed. Okay, and then there's this R squared of the model here that we can see, along with a number of other output that the question's not asking us to have a look at, so I won't spend any additional time explaining them. And so which of the following is the best interpretation of the R squared value that we have here as calculated above? Okay, so they're all 75% of something. It's explaining 75% of something. We can see that here. But we need to figure out, well, what is that 75 referring to? And the correct answer is that R squared is used to measure the variability in what we're trying to predict. And so what it is like we've built a model, we're trying to predict total annual salary. How much of the variability, just that differences that we just naturally see in what we're trying to predict, does our model actually explain? What does it actually account for? So in this case, we actually find that 75% of the variability in those total annual scores can be explained by the number of years in employment. That sounds pretty good. You can maybe go back if you want some more information on R squared and have a look at some of the previous lectures. But essentially, you just need to remember that R squared is assessing how well our model is accounting for the variability in what we're trying to predict. Okay, question 7. We have a model that has a reasonably high R squared, but we should first check that the model is a good fit for the data using a graphical diagnostic. So having a look at the residuals versus the predicted values. Okay, so which of these is false about residuals versus predicted plot that suggests that the model is a good fit? So here we're just again saying that if we've got a good model, it shouldn't have any pattern in the predicted versus the residuals. Okay, and one such pattern that could happen is a fan-shaped pattern, which would essentially start out very thin over to the left side of the plot In fact, I've already got the plot for the next question here, so we could use this as an example. So it'd be thin here and then fans out, which would essentially say that as our predicted total annual salary increases, our model's performance decreases because the residuals become larger and larger, meaning that our prediction gets further and further away from the actual value, which sits at 0. That's not the sign of a good model. We don't want our model to maybe be making systematic errors, particularly systematic ones where if our predicted annual salary gets larger, that it just increases. So that's what's happening here, is that it's saying we don't want to see a fan-shaped pattern. All these other ones are true about what we do want to see. We don't want there to be a pattern. We should hope that they're randomly scattered, meaning that the errors that our model's making is randomly scattered around 0. We're not always predicting too high. We're not always predicting too low. And there's no particular pattern. And we also don't want there to be really distinct clusters of points as well. For the same reason, that would mean that our model's making some sort of systematic error here. So if we have a look at question 8 as well, is to use to create the actual plot. So, predicting our total annual salary for a number of years. And this is the same model we've been using before. So first we need to augment. And if you don't remember what augment is, if you go back to lecture 4 of week 8, Mina introduces that. And it's a way of fitting our model and getting a number of different metrics to assess how that fit has gone. And so we use our augment. We can view the names of our variables, which is here. And this was just used here to help you identify in the ggplot what you're going to need to make this plot. And again, actually the answer, if you go back to week 8 and lecture 4, you can actually see that Mina uses this IDS fitted versus the residuals. The fitted in this case is what they're referring to, the predictions of the model during fitting. So you fit the model first, and then these are what your model has predicted for those values. The residuals here being how off were the actual predictions. Were they too high or were they too low? And, ideally, they're not too high, they're not too low. If they were perfect, they'd be 0. But, if they all fall on this 0 line, then we might be suspicious. Like, why is our model predicting everything 100% correct all the time? That suggests to me that it's probably overfitting. So we do want there to be some fluctuations around this 0, and there not to be some sort of systematic error. Now, in this case, it looks really bad. It looks like we're under-predicting here by quite a lot. And then we're over-predicting, and then we're under-predicting again. So when we have a look at what are our choices here, we can see that the answer is actually that the residuals do initially increase as predicted values increase, and then decrease as then they also then get to a certain threshold, and they start to decrease again as predicted total annual salary is increasing. This is a discernible pattern here. Like, we can clearly see there's something happening in this model. And this is suggesting that it's not a good fit, because it's going to be making systematic errors depending on, what the total annual salary that we're trying to predict. It's probably going to under-predict low salaries and over-predict and under-predict these high salaries too, and over-predict salaries in this kind of range here. So although we had a very good R-squared, one metric is never going to be enough to fully understand our model. You always want to be checking multiple parts of your model, in this case looking at the residuals, looking at the R-squared, and looking at some other performance metrics that we have discussed in prior weeks and will be discussing this week, to get a kind of holistic view of how your model is performing. Because if you only ever use just one metric, such as R-squared in this case, you might have an overly optimistic view of how good your model is, and you might not be getting the full picture. All right, so what are we doing this week? Well, this week we're going to start by having a look at cross-validation, and we're going to be using cross-validation to help us, again, build better models by using our training set, and splitting it up and doing lots of different repeated versions of testing our model and to see how well it's making predictions on what are known as validation sets. And this means that we can leave our test set alone until we're at the very end and we're happy with our model, but we split our training and validation sets and see how our model is doing on different bits of the data to help reduce the chance of our model overfitting, or at least getting a better idea of how well our model is fitting and if it is being influenced by overfitting. There's a number. Mina's going to go through the application exercises, and then we have a look at quantifying uncertainty and bootstrapping. And so what that lectures are about are essentially, we've got an idea of what our slope is, but is there any uncertainty around that? Like, how certain are we of that slope being accurate? Can we get an idea of the error that might be there, and to see if we can then use that to inform how confident we are in our model. So for the assessments, I've already talked about what we're expecting this week from homework 4. The lab this week is not going to be marked. It's just working on the projects again. And obviously for next week is the big deadline on Friday for the project itself. Now, as part of that, we're going to be asking you to do a peer evaluation. And at the time of recording, I haven't got this up because I'm just like making some final changes to it. But you do need to do the peer evaluation for your teammates. I know it's been optional for most weeks. This time it's not optional because we want to get an idea of how much each individual in your team contributed, and that'll affect their grades slightly depending on what you say and reflect on the team. You can look at the breakdown of how the marks work in the assessments on the projects as well, if you're interested how that will actually contribute as well. Now, Lab 8 also goes into a little bit more detail into how we're going to be marking the labs, the presentations and other stuff. So have a look there if you're wanting a little bit more of an insight into more specifics of the mark scheme that we're going to be using. And there are a number of interactive R tutorials as well, which will be useful for homework 5, which is going to be due in week 12. It's your last homework you need to give us. I'm looking forward to seeing you as always in our interactive sessions, and have a good rest of the week. Bye-bye.